Hello there, and welcome to Lecture 23 on the ratio and the root tests. So these are our final two tests that we're going to be covering in this series section of this course. The first part of this video is going to be the ratio test, and I'm going to do a couple of examples. And then the second half of this video is going to be the root test, and we'll do a couple of examples. So let's first talk about the statement of the ratio test. So you're going to let sigma a sub n be any series. And then there's three different things that you need to know for the ratio test. So the first one is if the limit as n goes to infinity of the absolute value of the a sub n plus 1 term divided by the a sub n term, if that is equal, we'll call that L, we're going to call it capital L. So if that quantity is less than 1, then the original series is absolutely convergent. And absolute convergence was what we talked about in the last video. So if you're not sure what it means to be absolutely convergent, you should go watch the last video for that. But as soon as you're absolutely convergent, that's like a stronger type of convergence, and it automatically means that you're convergent. So for this test and for the root test, you're testing whether something is absolutely convergent. The second one here says if this limit, which we called L, if that's greater than 1, then the original series is divergent. So that's the second case. And then the third case is, well, if this limit that we've called capital L, if it's exactly equal to 1, then this test is inconclusive, and you'd have to go try a different test to figure out if it's convergent or not. All right, so let's use this ratio test on a couple of examples. So here's my first one. So this right here, the whole thing is called a sub n, just like I've been calling it for this whole unit. So what we need to do is we need to consider capital L, which is the limit as n goes to infinity of absolute value of a sub n plus 1 divided by a sub n. So this is the limit as n goes to infinity, absolute value. And what you do is you take the original a sub n formula, and for all of the n's, you plug in n plus 1. So you're going to get a giant fraction. And in the numerator, you're going to do that. So plug in n plus 1 for every single n you see, and you get, I already don't like how I wrote that, so give me a second to erase that. So this is going to be negative 1 to the n plus 1, n plus 1 to the third, and then the last n I see is divided by 3 to the n plus 1. So in the numerator, you plug in a of n plus 1. The denominator is a sub n. So this is just the a sub n formula you started with. So that's negative 1 to the n cubed over 3 to the n. OK, so we're going to see what this equals. So this is the limit as n goes to infinity. First thing I should point out is these absolute value bars are going to get rid of negative 1 to any power. So both of these disappear because of the absolute value bars. Also, because n is some positive number, 1, 2, 3, 4, all the rest of these terms I have left, they're always going to be positive numbers, right? n plus 1 to the third, 3 to the n. All these are positive. So at this stage, we can get rid of the absolute value bars because this whole thing in here is going to be positive. So we're just going to get n plus 1 cubed divided by 3 to the n plus 1 all over n cubed divided by 3 to the n. OK? Now we have a fraction divided by a fraction, so we're going to do basically keep the first fraction, and then flip the other fraction, so 3 to the n over n cubed. And then we're going to do some algebra here. So a lot of the algebra steps are very similar for ratio tests. So once you've seen one trick, you've seen it pretty much in all the other problems. This exponent can be split up, and I'm also going to rearrange this. So I'm going to switch around the positioning here. So this is n plus 1 to the third over n cubed times 3 to the n over, and then this can be split up into 3 to the n times 3 to the first power if you use your exponent rules. And then notice these cancel. And I just have a 1 left on top. So then this is going to be the limit as n goes to infinity. What happens with this? Well, they're both cubed. The highest power for both of these is cubed. So we take the ratio of the leading coefficients, and this limit right here, that's just going to be 1, because you get n cubed over n cubed. So this is 1. And then here I just have a 1/3 left over. So this limit is 1/3, which is definitely less than 1. So that means that the original series, it is absolutely convergent. And I would say absolutely convergent by the ratio test. OK, so there's an example of one that converges. For this next example, what I'm going to do is I'm going to remind you of a very special limit, because this comes up a lot during ratio tests. So I need you to have this background knowledge so you can do other problems later. So let's take a look at this. So this is a calculus 1 limit. So you might remember this from calculus 1. I might not know how to spell calculus. I wrote calcus. Oh, goodness. OK, so calculus 1 limit. And if you don't remember this, don't worry. We're going to go over it right now. So this limit of n plus 1 over n to the n, that's equal to e. So the way I would do this in calculus 1 is I'm going to let y equal the limit as n goes to infinity. And then this is going to be n plus 1 over n to the n. I'm going to take ln of both sides. So if I do that, I have the limit as n goes to infinity. And then if I have ln, I can bring an exponent in front. So this is going to be n times ln of n plus 1 over n. So the whole reason we took the log of both sides is because I can bring that power down. And then for this, what I'm going to do is I'm going to keep writing this out. So this is the limit as n goes to infinity. I'm going to rewrite this. This is n, or ln of n plus 1 over n divided by 1 over n. So I rewrote this n times this as dividing by 1 over n. It looks different, but it actually is equivalent to this. And the idea is if I take n to infinity now, I get ln of 1, which is 0, and then I get 1 over something going to infinity is 0. So I get 0 over 0 for this, which means I can use L'Hopital. So that means I'm going to take the derivative of the numerator and denominator separately. So the derivative of the numerator here is 1 over what's inside ln. So that just means you flip it. So I get n over n plus 1 times the derivative of the inside. Well, notice that n plus 1 over n, that's equal to 1 plus 1 over n. You just take the n and write it out like that. So what's the derivative of this? Well, that's just going to be negative 1 over n squared. So that's the derivative of the numerator. And then the derivative of the denominator is, because that was what this derivative was of the thing over here, this is negative 1 over n squared as well. So these cancel. And then this limit right here, n over n plus 1, goes to 1. So if you follow my equality all the way back, I have ln of y equals 1. If you take e on both sides, base e, you get y equals e. And just notice for this example, I treated n as a real variable. So I took a derivative. This is a continuous function in n. So just know that my domain, this was a continuous function. You can think of this as just like x. But my n, the domain for my n here was not just 1, 2, 3. This was all real numbers, where it made sense for this. So all numbers greater than whatever would keep this defined. Anyway, so that's why this limit is e. And now I'm going to need that for this next problem. So we're going to do the ratio test. So I need L equals the limit. This is my a sub n right here. So I have the limit as n goes to infinity. My a sub n plus 1 is going to be plugging in n plus 1. So this is n plus 1 factorial over n plus 1 to the n plus 1. Remember, every single n needs n plus 1. And then you're going to divide this by n factorial over n to the n. So that was a sub n plus 1 divided by a sub n, just how we started the other example. Now for this, I'm going to go ahead and flip this. And notice, again, all of the n's are positive, so all of this is going to stay positive. I don't need the absolute values anymore. So this is going to be, you're going to keep the first fraction. I'm going to flip the denominator. And then that's what I'm looking at right now. So we need to start splitting these up. So let me show you the typical algebra things we do when we split these up. So first, n plus 1 factorial is n plus 1 times n minus 1. So this is all the numbers starting from n plus 1, and you're multiplying all the way down to 1. Maybe I should say here, recall that n factorial is n times n minus 1 times 3, 2, 1. It's all the numbers starting from that number and going down. So this right here is actually n plus 1 times n factorial. So we remove the largest one, which is n plus 1. But then you still have n and all the rest of them, right? So that's what this turns into. This is times n to the, this is times n to the n. So n to the n. Here I'm going to use that exponent rule I used before for the 3 here. So n plus 1 is the base. So I have n plus 1 times n plus 1 to the n. And together, if you multiply those together, the power adds, and you get n plus 1 for the power again. So I split those up. And this is times n factorial right here. So the n factorials cancel. And also the n plus 1s cancel. And you're left with the limit as n goes to infinity. Both of these are raised to the n. So I could say this is n over n plus 1, all raised to the n, because they're both raised over n. And that's everything I have left. What's the difference between this and the limit I just proved? It's flipped over, right? This is n plus 1 over n, and this one is n over n plus 1. So this is the same thing as the limit as n goes to infinity. If you flip this, if you were to flip that, what algebra thing do you have to do? How do you flip a fraction? Well, you raise it to a -1 power. So in order for me to flip that and keep it equal, you need to raise it to a -1 power. And now, the limit of the inside thing right here identically matches what I have before. So this is e, but then I have to raise it to a -1 power. So that's what L equals. So this is the same thing as 1 over e. E is like 2.7, so this is definitely less than 1. So that means that the summation of a sub n is absolutely convergent. OK, let's give this final one a try. So here I have my a sub n. After you do a bunch of these, it should start becoming routine. So my limit is, the limit is limit as n goes to infinity. I'm going to give myself plenty of room for this one. So a sub n just gets plugged into the denominator. So let me just do this in a different order this time. I hope you don't mind. So that's my a sub n. And I have to write now a sub n plus 1 in the numerator. So that's going to go right here. So I'm going to plug in n plus 1 to both of the spots I see. So I get 2 times 4 times 6 times 2n times, and then what would the next one be? If you plug in n plus 1, you get 2n plus 1, like that. So what's happening in the numerator is you're just multiplying all the even numbers up to 2 to the n, and now I've multiplied by the next one. And then here's another n, so you've got to plug in n plus 1 to that. So now here's the n, a sub n plus 1 over a sub n. So that's what I have right there. All right, just like the other ones, often this is true. You're plugging in positive numbers for n. So I don't need absolute value bars anymore, right? They're all going to be positive numbers. Let's try to cancel things right now before I have to flip this whole monstrosity, OK? So you see how in the numerators, you have all of these things are the same. The entire numerator cancels out here, and all of this does. So you just have this one left. So this is going to be 2, and let's distribute that too. So we have 2n plus 2 divided by n plus 1 factorial. Now I do keep, change, flip this bottom fraction. So what's left if I flip this? It's just this n factorial over 1, because all of this canceled. But we can handle that, because we just did something like that in the previous example. So this is the limit as n goes to infinity. 2n plus 2, you can break up n plus 1 factorial just like I did before. It's the highest number, n plus 1, the highest factor, and then n factorial, the rest of them. And this is times n factorial over 1. But then those n factorials cancel out. So I get the limit as n goes to infinity of 2n plus 2 over n plus 1. The degrees of these match. What's the ratio of the leading coefficients? It's 2. But that's larger than 1. So we have a divergent series. So this is divergent by the ratio test. OK, so there was an example of one that actually diverged. In the next half of this video, we're going to be doing a very similar process for the root test. So I will see you soon. All right, welcome back. So now we're in the second half of the video, which focuses on the root test. So again, let summation a sub n be a series. You're going to notice, and I want to point this out now, that the rules for the ratio test are identical for those of the root test. The same values for L give you the same conclusions. So you don't have to memorize two separate things here. You're going to be able to pair them up, and all the conclusions are the same. So basically, look at what we wrote for the ratio test as we go, and you're going to see that they're parallel to each other. So the first one is if the limit as n goes to infinity of the nth root of absolute value of a sub n is L. So here we have a new thing we're looking at, a new thing we're calling L. But if it's less than 1, then just like before, the original series is absolutely convergent. And remember, that automatically means then that the original series is convergent. So there's this case. There's case number 2 here, where if this new thing we're examining, this nth root of a sub n, if that's greater than 1, if that limit's greater than 1, then the original series is divergent, which is the exact same conclusion we had for ratio test. And then the last one here is if this capital L nth root of the a sub n, if that's equal to 1, the test is inconclusive. Yet again, the same as the ratio test. So you try a different test. OK, so let's look at this first example. So we have this right here is our a sub n. It is 2n plus 3 over 3n plus 2, all raised to the nth power. So a dead giveaway that you have to use the root test is if you see a whole factor raised to an nth power. And usually use the root test. So let's plug into the formula here. So we have capital L is the limit as n goes to infinity of the nth root of. Now, it's the nth root of a sub n under the absolute value bars. But if you plug in all these positive numbers here, it's always going to be positive. So I don't need the absolute value bars in this case. I can just plug this in as 2n plus 3 over 3n plus 2 raised to the nth power. So I plugged in my entire a sub n under the radical. And now if this helps you to see what's going on, or if this helps you with future problems, I will do that. So here I have 2n plus 3 over 3n plus 2 to the nth. However, taking the nth root of something is like raising it all to the 1 over n power. You know what I mean? So if you have the square root of x, that's x to the 1/2 power. So if you put an n here, an nth root would be 1 over n power. So this is what I'm thinking. So now you can really see that if you multiply these together, they cancel out. An n and 1 over n cancel out. And you're going to get the limit as n goes to infinity. All that's left is 2n plus 3 over 3n plus 2. They're both degree 1, the numerator and denominator. Take the ratio of the leading coefficients, and you get 2 over 3. Which is less than 1. So the conclusion means that that original sum, a sub n, is absolutely convergent. Convergent. And that's by the root test. Okay, so there's that first example. There's an example, one that converges. Just like before where I gave you that important limit, here's another thing that's going to really come in handy, this type of limit, when you're doing this test. So the limit as n goes to infinity of a to the 1 over n for any real number, any real constant a that's not equal to 0. So this limit is 1. So I'm saying that limit is 1. And what I'm going to tell you, because I'm not going to do it for you here, I'm going to say, follow my example. Follow my example in the first part of this video for the limit as n goes to infinity of n plus 1 over n to the n equals e to prove this. And I'm going to leave it up to you, because you can follow the same process I gave in the first part of this video to prove that that's 1. So you should go, maybe pause the video, go prove that that's 1. That would be good for you to do. Let's take a look now at this second example. So in this example, you'll see that there are a lot of powers that have n involved. So once again, that's kind of our giveaway that it's going to be the root test. So for the root test, we have to consider the limit as n goes to infinity of the nth root of a sub n. It would be under absolute value bars, but again, all these positive numbers you're plugging in will always have a result of having a positive term. So I don't need absolute value bars. It's going to be n to the n over 3 to the 1 plus 3n. Let's start manipulating this a little bit. So this is the limit as n goes to infinity. Just like I said over there, I'm going to have this nth root is going to give me everything raised to the 1 over n power. This is going to be n to the n, not 2. This is going to be n to the n. And then I'm going to split this up using exponent rules. This is going to be 3 times 3 to the 3n. So what I've done is I've just split this addition up using exponent rules. Now what I'm going to do is I'm going to do another rule for exponents. So this 1 over n power, I'm going to distribute that to all of these power. I'm going to do a power to a power. So here I have n times 1 over n gives me n. I have 3 to the 1 over n if I distribute to there. And then 3n times 1 over n just gives me 3. So I've distributed this to every single one of the powers. And now I notice that here I have 27, just 27. So I could factor out 1 over 27. It's going to be 1 over 27 limit as n goes to infinity. What's left? I have n over 3 to the 1 over n. Now let's take a look at that rule I just talked about. So any constant to the 1 over n, that goes to 1. So this time, my a is 3 in that rule over here. And that means that this piece, that goes to 1 based on my rule. So this is going to be 1 over 27, the limit, as n goes to infinity, of n over 1. But what happens with that? I have a constant times infinity here is in the numerator. So this is going to go to infinity. This equals infinity, which is certainly larger than 1. So this series, the original series, is divergent by the root test. So there's an example of one that diverges. Let's take a look at this example now. So again, both of these are raised to the n. So what I'm going to do is I'm going to do the root test. The way you do that is you do the limit as n goes to infinity. We have the nth root of, what is the absolute value of a sub n, which is this. This time it actually matters. So if you take the absolute value of this, the absolute value of a factor of -1 to the n power, that's just going to go to +1. It's going to turn all of those into positives. So the absolute value of this, you turn the -1 into +1. And then here, if you're plugging in numbers larger than 1, think about the arctangent graph for a second. I've drawn it enough for us. If you plug in any number larger than 0, you get a positive number for arctangent. So that means all of these are going to be positive. I'm going to have positive numbers raised to a positive. So all of this is going to be positive. So I have arctangent of n to the n. So I plugged this into the root, but I just changed my -1 into +1 now because it's absolute value. This is the same thing as the limit as n goes to infinity. I'll say that this is all raised to the 1 over n of 1 over arctan of n to the n. Now we'll distribute these to each of these. So this is equal to the limit as n goes to infinity. I have 1 to the 1 over n. And distribute it to this one. This was raised to the n. This will cancel with the 1 over n. I get arctangent of n. This time my a is 0, but it's 1. Sorry, my a is 1. So we use this rule right here. 1 to any power is going to give me 1. So as n goes to infinity, that goes to 1. I have my arctan graph almost drawn fully over here. What are the asymptotes? What are the horizontal asymptotes for arctangent? They're pi over 2 and negative pi over 2. So as n goes to infinity for this graph right here, it goes to pi over 2. So 1 over pi over 2, if you flip that over, that's 2 over pi. And then the final question for you, is this bigger or smaller than 1? And it's smaller than 1 because I have 2 over 3-ish, 3.14. So this is less than 1. What conclusion do you make? That means that the series is I almost wrote the wrong thing. Absolutely. I did write the wrong thing now. I just can't spell. Absolutely convergent by the root test. All right, and there are examples of the root test. So I hope this helped you. I even give you a couple rules that you should maybe make into flashcards. That might be good, because you're going to encounter these limits as you do ratio and root test. All right, in our next video, I'm going to summarize all of the different series tests we've seen, and I'm just going to mix together a bunch of examples, just like I did for the summary of the integral thing, like the integration techniques. So I'm going to do the same type of video for lecture 24. I look forward to seeing you then. Have a nice day.